Welcome back to this lecture on the proof by cases. In this third segment, we're going to show a slight variation on this proof technique. In the previous segment, we were trying to prove a theorem of the form for all x p of x. Now, let's take a slightly different form for the theorem to be proved. Let's say it's a conditional of the form for all x, p of x implies q of x. So you could try and use a direct proof or an indirect proof of these kind of theorems as we discussed in earlier lectures. However, sometimes these techniques don't get you very far because you don't have enough information to get started, even by assuming, say, p of x. So sometimes, however, you have additional information about p of x. For example, what if you knew that the following proposition is true, namely, for all x in the domain, the same domain as in the theorem, p of x is equivalent to the following disjunction, p1 of x or p2 of x or pn of x. Well, what that means in particular is, since this is true for every element in the domain, p of x can always be replaced by this disjunction. So how can we use this fact to make it easier for us to prove this theorem here? Well, we can use the following logical equivalence that you need to get comfortable with. This equivalence says that if you have a conditional where the hypothesis is the disjunction of the propositions p1, p2 through pn, and the conclusion is q, this conditional is logically equivalent to this conjunction of conditionals, namely p1 implies q and p2 implies q and ... through pn implies q. So the reasoning here to apply the proof by cases is that in order to prove that p of x implies q of x, and we kind of get stuck with the other proof techniques, but we know that p of x is equivalent to this disjunction. Therefore, we are entitled to replace this theorem for all x, p of x implies q of x, with a theorem of the form for all x, p1 of x implies q, and p2 of x implies q, and etc., pn of x implies q. In other words, we can replace this single proof by n subproofs, where the first subproof is case number 1, assuming p1 of x holds, we try to prove q. The second case corresponds to the assumption that p2 of x holds implies q of x, and so on until we get to case number n. And that is the new template we're going to consider in this segment. And to illustrate the use of this template, we're going to consider another example, theorem number 2, which, by the way, is the same theorem as number 8 in the previous lecture. It states that every perfect square is either a multiple of 4 or is of the form 4 times I plus 1, where I is an integer. So what this is saying is that every perfect square is either of the form 4 times I, where I is an integer, or it's 1 more than a multiple of 4, 4 times I plus 1. First, you should convince yourself that the statement of this theorem follows this pattern. It says, for all x, if x is a perfect square, so p of x means x is a perfect square, then it must be the case that either x is multiple of 4, that's q1, or x is of the form 4i plus 1, that's q2. So in this particular case, the proposition of the propositional function q of x is replaced by a disjunction of q1 of x or q2 of x. But of course, the proof by cases applies or breaks down the cases over the hypothesis p of x. So we can still apply the proof by cases technique here by applying cases over p of x. So let's do it. Let's start our proof by cases of this theorem. First, it's a universally quantified theorem where x ranges over the set of all the integers, say. So let n denote an arbitrary integer. We're going to make the assumption that p of x is true, and we're going to try and prove q of x. P of x is the assumption that n is a perfect square, which by definition means that there exists a positive integer p such that n can be written as p times p, or p squared. So what remains to be proved now is that p squared is either a multiple of 4 or is of the form 4 times I plus 1. Now this is another situation where it is not obvious how to get started to reach that conclusion. So it would be nice if we had more information about n or p. And this is a perfect example of when the application of a proof by cases can be helpful. Sure, we don't have any more information, say, about p, but we can find new information. For example, if we knew that p was odd, then maybe that would help us infer the conclusion we're after. But of course, we don't know that p is odd, but what we do know is that p is an integer. In fact, it's a positive integer, so it must be either odd or even. And that is these are the cases we're going to consider for the rest of the proof. So case number 1, p is even. By the way, before I start the proof, let me go back to the template and make sure we understand how this works. So what is p of x here in the template? That's the hypothesis of our conditional, which is x is a perfect square. So the cases we are using here, there are 2 of them. What are they? Well, what we are assuming, or what we know is true, is that p of x is true, meaning x is a perfect square, is equivalent to a disjunction of 2 cases. The first case is that x, so here p of x means x is a perfect square. So it's the square of some positive integer. We know that that's equivalent to x is a square of a positive odd integer, or x is a square of a positive even integer. And these are the 2 cases we're considering now. So again, n is the square of p, so it's a square of a positive integer, and let's assume that integer is even. So we are dealing with the first case where n is the square of a positive even integer. And from that, hopefully we'll be able to infer the conclusion q of x of our theorem. So by definition of being even, p must be written as 2 times k for some integer k. Now we have an expression for p as 2 times k, and n is p squared. So we can plug in the expression for p to obtain 2 times 2k squared. We can expand this out to get 4 times k squared. And we notice that this is 4 times some integer k prime, since if k is an integer, k squared is also an integer. So what can we tell about n if it's equal to 4 times some integer k prime? Well, by definition, that means n is a multiple of 4. Now, are we done in this case? Have we proved the conclusion of the theorem? Well, not quite, because the theorem says q of x is true. And what is q of x in our case? It's really a disjunction, q1 of x or q2 of x. So what did we just prove here? That n is a multiple of 4. Well, we basically just proved q1 of x. So we're almost done, but not quite. However, the easy part here is that whenever q1 of x is true, then by a familiar logical equivalence, you know that q1 or anything is true. And here we're going to pick as q2, of course, the one that we want, this one. So in conclusion, knowing that n is a multiple of 4 allows us to infer that, well, n is a multiple of 4, or n is of the form 4 times I plus 1. And that is the conclusion of the theorem, which means we're done with case 1. Let's now complete the subproof for case 2, which will be very similar. Remember, in case 2, we assume that p is odd, which means there must exist an integer k such that p is equal to 2 times k plus 1. From that, we can conclude that n, which is equal to p squared, is equal to 2 times k plus 1 squared, which, when we multiply that, we get 4k squared plus 4k plus 1, which is the same as 4 times k squared plus k plus 1. And here, notice, because k squared plus k must be an integer, since k is an integer, the form of n is exactly what we want, namely 4 times an integer I plus 1, where I is some integer. So in conclusion, if p is odd, we just prove that n must be of the form 4i plus 1. That is not quite the conclusion that we want, but since we proved the second element of the disjunction here is true, we could just add any operand, first operand to the disjunction. And of course we add the one we need, namely q1 here. So again, proving that n has the form 4i plus 1 is enough to infer that it has the form 4i plus 1 or anything else, namely or multiple of 4. And again, that is the conclusion of our original theorem right here. So don't forget to properly terminate the proof. Now that we have proved the result in both cases, we must state so. So in all cases, n is a multiple of 4, or n is of the form 4i plus 1. And finally, let's use universal generalization to generalize over the set of all integers to conclude that for every integer, if the integer is a perfect square, then it is either blah, blah, blah. I cut it short here, but you know the conclusion of the theorem. So this concludes our second example of a proof by cases, where the theorem we're trying to prove is not for all x p of x, but it is of the form for all x, p of x implies q of x. So this proof looks a little bit complicated, but I want to convince you here to conclude this segment that it's really just the combination of a couple of techniques you already know. First of all, to prove the conditional p of x imply q of x, we have used a direct proof, namely we assume that p of x is true and we try to infer q of x. The problem here is that assuming p of x, namely that x is the square of some integer, was not enough to infer q of x. So what we did is we introduced an extra condition and say, well, let's assume that x is not just the square of an integer. Let's say it's the square of an odd integer. And that was enough to allow us to prove q of x. But of course, that's a different hypothesis. So we must also consider all the other possibilities, namely that x is the square of an even integer. And since these are the only two possibilities, either it's a square of an odd integer or it's the square of an even integer. There's only two cases to consider. And since in each one of these cases we were able to prove q of x, by using a proof by cases that covered all possibilities, we were able to complete the proof of the original theorem, which did not have the cases explicitly stated.